Okay, so we're up and running. Here's where we left off. So more integrals we're going to do. Again, the context is we're talking about double integrals, and in particular we're talking about double integrals over non-rectangular domains, where the big question is how do you figure out what the bounds ought to be. Okay, so another example. There's a kind of a moral to this example. I'm going to rewrite a double integral as two separate iterated integrals, and then we're going to sort of post-game and decide, wait a minute, which one do we like better, and how can we make the good thing happen that we want to happen, and how can we avoid the bad thing? Okay, so first, here's the integral. It is an integral whose domain is bounded by this curve and this curve. Now I want to very quickly take an aside and talk about the language here. In particular, what do I mean by the term bounded by? This actually means two things. On the one hand, it means that these two curves make up the boundary of the shape in question. And you might think, okay, well then of course, now clearly we're talking about this. But how do you know, as a reader of this question, how do you know I didn't mean this region up here? Right? That region there, the boundary consists of, well, the green curve and the blue curve, and why isn't that it? Right? And the answer is bounded by means a second thing. It means that the region is actually bounded. And bounded means it doesn't run off to infinity in any direction. Another way to say what we mean by bounded is that you can draw a circle around it. Right? And I can draw a circle around this region here. There we go. Right? But you can't draw a circle around something that goes off to infinity in some direction. Okay. Now again, that's just a point of language, but it is important. Make sure when you're on a test or looking at a homework exercise that you interpret the question correctly, because that is part of the question. Okay, so now for no particular reason, I'm going to slice in this order, and off we go. Let's see, x. There's the x-axis. Here's what x slices look like, and with that in mind, it's pretty easy to see how I will find the bounds. The lower bound is at that point. Now, I'm going to have to do a little bit of algebra on this one. How do I figure out what the x-coordinate of that point is? That point isn't given. Right? But I can see that that point is on these two curves, which have these two equations in which I can solve for x, because x is what I'm trying to find. Solve for x in these equations. You actually get a couple of candidates, right? Notice that when you solve for x in these equations, as far as the equations alone are concerned, x could be 2 or negative 2. And you've got to then look at the picture and figure out, well, wait a minute, of the two algebraically admissible options for these equations, which one is the lower bound that I'm actually interested in? Right? And again, the picture will usually be the key tool here. So make sure you interpret appropriately from the picture and that you pick the correct bound. Okay. Now, very similarly, how would we find the upper bound, right? Where am I going to get this upper bound from? Well, it's this point, which is on the same two curves, which therefore has the same two equations in which, again, I solve. Now, this time, though, I pick plus 2, because, again, thank you, picture. The picture indicates that, well, clearly I want the one that's further to the right. I can, again, see from the picture, I want the one that's positive, right? But you have to, again, make the correct choice. How are we doing? Is everybody happy with that? Okay, so now what about, though, the inner bounds? The inner bounds come from fixing a value of x, right? We're now going to look at the range of values for y. Y sort of moves along that x slice. Y is going to go from y1 to y2, as it were. Okay. Let's take these one at a time. How am I going to find the lower bound for y? Well, that corresponds to this point, which is on this curve, which has that equation. Always pause at this moment and remind yourself, what are you here for? Why am I interested in this equation again? Oh, right, it's because I'm interested in a y bound. So make sure you solve for the correct variable. Here in this equation, I need to solve for y, which is nice, right? Because it's already been solved for, and I can see it right there. It's x squared. Okay, everybody good? All right, now let's look at the upper bound. And y'all are starting to notice the pattern, I'm sure. The upper bound, y2, comes from this point, which is on that curve, which has that equation. Now, what do I do in that equation? Again, reminder, I always have to remind myself, don't forget, I'm looking for a y bound, so I need to solve for y in this equation. And again, easy to do, lucky break. Sometimes everything just lines up. Okay. And there we go. Okay, so no problem. Now, I'm going to do the same question again. This time, though, instead of dy dx, I'm going to do dx dy. And let's just see how things turn out differently. And I'm going to move a little bit more quickly here. Let's see here. What's the range of values of y for these y slices? And this actually is a kind of a immediate. The lower bound is obviously where y is equal to 0. It's the bottom of a parabola. The upper bound is clearly on that curve where I can just straight up see what y is, right? So the outer bounds, no sweat. What about the inner bounds? The inner bounds come from fixing a value of y, thinking then about the range of values of x, identifying that that range of values comes from, well, these 2 points. And again, we play the usual game. Those points are on this curve, which has that equation. Again, slow down. Here's a landmine. A lot of students will step on this landmine. A lot of students will see, oh, this curve, that equation. So the upper bound, and look, I guess it's x squared, right? And then they'll see, well, wait a minute, but is this the lower or the upper? And then students will start to get creative and think, maybe it's negative x squared to x squared? I don't, something like that. Completely wrong. 100% wrong. Students are not following the rule. You got to follow the regimented procedure. We are trying to find bounds on x, right? We're looking for x bounds. So we have to, in this equation, solve for x. Give me how x is a function of y. And if you solve for x in that equation, then you get plus and minus square root of y. Is everybody happy? Okay, so absolutely 100% pure D wrong if you put x squared in these inner bounds. Is everybody totally happy with that? Okay. Okay, so these are the two options, and you get to choose either one you want. Now, obviously, this is, you want to pick the choice that's going to make your life as easy as possible, right? This is always a good thing. Try to make the best, easiest possible choice. So I have a preference between these. I like this one. There may be some counter examples, right? But frankly, I don't like square roots. And hopefully and presumably you don't like square roots either. I'll point out that it's particularly bad that these square roots are in the inner bounds. Because now let's think what's going to happen when I compute this inside integral. When you compute this inside integral, you're going to play certain games and find the anti-partial with respect to x, the blah, blah, blah. There'll be some formula there into which you're then going to plug in some square roots. Which means that this expression right here, that inside integral, your integrand for your outside integral is going to be an ugly expression involving square roots, and nobody wants that. In most cases, counterexamples granted, right? But that's why this is particularly bad. Is everybody okay with that? Does everybody see what I'm talking about? Okay. So when you are looking at a situation like this, that's what you want to avoid. Now let's ask the question, how do we avoid this, right? How can I want to have, without having to write them both down, right? Is there any sort of tip-off that, I should do it this way to get the more desirable result? And here's my take. Right? This is just my point of view on it. But where did these square roots come from? These square roots came from the fact that I had to solve for x in this equation. Ultimately, that's where the square roots appear. Why did I have to solve for x in this equation? It's because dx was on the inside. Right? So, on the other hand, why did I get something nice and pretty in here? Well, it's because up here in this first example, I had to solve for y in that equation, which I'm perfectly happy to do because no action required and there's no square roots. Right? So, roughly speaking, my strategy is this: whichever variable, looking at whichever is the weirdest equation that you face, whichever variable you would rather solve for, put it on the inside. I think it's a nice, pithy, easy to recall, easy to understand strategy. And if you follow that strategy, I'm not saying it'll always be the best. It's not always a win. Nothing's that simple, right? There's all exceptions granted. But if you follow this strategy, you will win overwhelmingly more often than you lose. Everybody good? Okay. All right. Another example with a moral. We've gone through this slicing process enough times that I'm going to start speeding it up, right? Because we have to, get on to the new points, right? All right, if you put the slicing in this order, your slicing is like this. You get a range of values for y. The inner bounds have x as functions of y. Details to follow. There's those inner bounds. Make sure you can do that, of course. Right? Now, on the other hand, suppose we slice in the other direction. And it's tempting to say that with x on the outside, I should start by saying x goes from 0 to 2. Here's the problem. If I do that, if I say x goes from 0 to 2, and then I ask what's the range of values for y? Well, for some values of x, this curve determines my upper bound for y. For other values of x, this curve determines my upper bound for y. There's two separate curves with two separate equations. Which one do I solve for y? Do I solve them both for y, and then do I average them or something? Right? It's not clear how I would fill in the blank of what this ought to be. Right? And the answer is I can't. As written, what I have to do is break this up into separate pieces. I have to say, look, x starts off by going from 0 to 1. And I'm going to stop at 1 because the thing is, for those values of x and only those values of x, this tells me what my upper bound for y ought to be, that my upper bound for y ought to be x. But then, subsequently, I got to keep going and recognize that for these values of x, between 1 and 2, totally different story. Totally different story in that it's no longer that light green line. Now it's this dark green line that determines my upper bound for y. And so I get a totally different formula for the upper bound for y there. Everybody see what happened? Okay, so again, we have this situation where obviously I had a choice between two different ways to order my differentials. Clearly one of them is better. Clearly one of them is less better, right? This is the one that we want to avoid. So again, I could write them both down every time, and after I was done with effectively twice as much work, I could then eyeball and see which one looks better. But let's try to strategize on how I can avoid this in the future. And here's my idea. Ultimately, I feel like the problem here, the reason that I had to break this up as a sum of two separate integrals, the reason I had to cut it is because as I was doing my y slicing, as I was doing my x slicing, where's my eraser? As I was doing my x slicing, perpendicular to the x-axis, slicing like this, I sliced through a corner. So try not to slice through corners. Right? It's exactly because I sliced through that corner It's because I sliced through where one curve meets a different and turns into a different curve, right? That this bad thing happens. So that, now again, this is not a perfect rule, right? But it's surprisingly useful, a surprisingly good batting average of keeping you on the right side of things. If you see a corner, try not to slice mid-process through that corner. Notice that our original slicing follows the rule. Our original slicing up here, we were doing Y slicing on the outside, and Y slices, will they start going through a corner? Well, we were starting a new integral there anyway, so no problem. Then no corners, no corners, no corners, and now it ends at a corner. No problem. I was going to end my integral there anyway. It doesn't cost me anything, right? So as far as the avoiding multiple pieces is concerned, I did not slice through any corners, and that's how we arranged for the good one. Yes?
Can you explain again how you got those bounds, like the Y to 2?
Yeah, let's talk after class about that, because I've got a yeah, no, it's totally fine. It's and I'm sorry, because I have to make all these tough choices about how to spend class time. So, but talk to me after class. Yeah. Okay. So, big lesson. Try not to slice through corners. Try to think carefully about what you're going to have to solve for, and very, very often this will guide you correctly on how to slice the best way. Okay. So, another little annoyance that you're going to face in doing double integrals is sometimes the domain isn't given and you have to infer the domain. So here's a nice example. We want to find the volume in between this paraboloid and this plane. And if you look at how those meet, and again, bounded by, I guess it doesn't technically say, but it says volume in between, right? So I think that's equally clear. But this is, that's the volume that I actually want to compute. It's this, reproduce it over here, this volume, like that. Yeah? All right, and the first part of this example is actually, it's pretty straightforward. I'm going to take this, I'm going to think about the fact that there is a shadow down here. That shadow I can break up into little pieces, and on each one of those little pieces I can talk about, well, how much volume is there in that little, twig like thing there, and the total volume is the sum of the volumes of the twigs. Right? So everybody okay with that? Much like the French fry argument I made previously, but to me this doesn't look like French fries. So anyway, so this part is okay. But let's talk about then how do I figure out what this shape is here? What is my domain here? Again, not given. Right? So the observation I'm going to make, I'm going to show you the right way to do it first, and then I'm going to show you a very common wrong approach, is a wrong word, but a wrong bit of nonsense that students write down sometimes, but that's very tempting. So the right approach is to say, look, we're trying to understand something. Sorry, I wanted to be in pencil mode. We're trying to understand something about certain points down here in the XY plane. For any point down there in the XY plane, I can talk about the value of z that comes from the paraboloid, right? And I can also talk about the value of z that comes from the plane, right? And now I'm going to make a geometric appeal. For points that are in the domain, these values are going to be different because you're in the middle of the domain, and that twig French fry like thing is going to have some height to it because these two z's are different, right? But at the points that I'm interested in, at the points on the boundary, the green height and the blue height will be the same. Does everybody buy it? Okay, so that's our foot in the door. What I'm looking for is cases in which, and let's see here, I'll do it like this. I'm looking for cases where this z and that z are equal to each other. Now you got to do a little bit of algebra and actually solve. Let's see if I can zoom this. Oh, come on, there we go. Zoom this out. You set those z's equal to each other. Each one you have to solve for. The green one, of course, is easy to solve for. It's straight up given. The blue one, a little bit of work, right? Nothing bad, but you do have to solve in the original equation for that z. And that gives you this equation down here, and it's all over but the shouting and the completing of the square. You may recall I mentioned before, it shows up sometimes underappreciated in high school algebra classes, completing the square. Yeah, you're going to need it. So make sure you're good at completing the square. Look it up on the internet if you have trouble. Come to office hours. I'll be happy to show you how to do completing the square. And then the final punchline is that the domain you can see is a circle. Is everybody happy? Now let me show you what a lot of students do wrong on this. And I get the temptation, and I don't know why it won't. There we go. The temptation is totally understandable. Very often students will look at this picture and realize that they want to know where the one surface intersects the other surface, and they figure that's got something to do with the equations, and then they just figure that, well, I guess I'd better set this equation equal to that equation. And I just want to point out, there is no such concept as setting an equation equal to another equation. It doesn't make any sense at all. Right? How would this make any sense in this situation? By the way, why would I be setting the right side of one equation equal to the left side of the other equation? Why wouldn't I just set x squared plus y squared equal to 7? Right? It doesn't make any sense. So please, again, I like to point out landmines as we move along, and this is I see this so often. And setting two equations equal to each other just doesn't make any sense. And just for fun, I like to point out this obvious example. Here's an equation, undeniably true. Right, here's another equation, undeniably true. Always. No counterexamples. What would happen if I set these equations equal to each other? Absolute nonsense. Right? Is everybody happy? So please try not to step on that landmine. There is no such thing as setting equations equal to each other. Okay, so that is section 5.2. We're going to move on now to 5.3. This is the fastest covering of a book section that we're going to see in this course, and possibly the fastest you'll see in any course. This entire section has kind of one idea in it worth mentioning, and I think this shouldn't be a section. I think this should be an example, and that's about it. But anyway, whatever. It's not my book. So the big idea is that if you are asked to compute, and I'm going to zoom all the way out here for just a second. If you are asked to compute let's get into the right mode. If you are asked to compute a iterated integral, one thing you could do is reverse engineer what the domain was, seemingly working backwards, turning an iterated integral back into a double integral. And then you could take that double integral and you could slice it up again, perhaps in the other order. Right? It wouldn't make any sense to slice it up, go right back where you'd been. Right? But notice here I've got my dx on the inside. Here I've got my dx on the outside. So this idea of working backwards, reverse engineering your original domain, and then slicing up in the other order allows you to turn one iterated integral into a different, seemingly different iterated integral. Now, let's talk about why would you be interested in such a thing. There we go. Looking at this one, the inside integral. The very first thing that I need to do, I need to be able to compute the antiderivative of e to the x squared with respect to x. And bad news, you can't in any practical sense without using power series, which you don't want to do. So we're dead in the water, right? We're up against a brick wall here for this integral. So that's a circumstance where it's pretty darn handy to be able to say, hey, you know what? Instead, just as well, I could look at this iterated integral, which at a glance, it's a little discouraging at first because you look at this inside integral and you think, well, again, with the e to the x squared, and again, I can't, am I allowed to do that? But now check it out. This is e to the x squared, but I'm doing a dy integral. And that makes that integral actually easy. This is a constant. We're doing an integration of a constant with respect to y. So easy integral, and then this x here gives me an extra factor of x right there. And now when I actually get to doing an x integral, I don't have the integral of e to the x squared. I have an integral of x e to the x squared, and that is perfectly doable by an easy substitution, and it all falls apart and we win. Everybody on board? So I think it's a nice little trick, clever trick. It comes up here and there. I wouldn't say often. I don't want to oversell it, but it does come up every sort of rare once in a while. All right. Okay. Moving along. Look how fast that was. We just covered section 5.3. 5.3. Okay. 5.4. Triple integrals. You can probably see this coming. Single variable integral, we're looking at a one-dimensional interval that we chop up into pieces. Why? Lots of reasons. There's a bunch of quantities that accumulate over intervals. Okay, double integrals, that's where I have a two-dimensional region, maybe a rectangle, maybe not a rectangle, but a two-dimensional region that I want to chop up into pieces and make a Riemann sum-like thing, two-index Riemann sum. Why? Because there's a lot of stuff that accumulates over two-dimensional regions as well. Okay, so what's a triple integral? Well, there's a lot of stuff that accumulates over three-dimensional regions. It's as simple as that. And so looking at the, okay, why won't this move? There we go. Looking at the picture here, here's a three-dimensional region. I'm going to start with a box, three-dimensional rectangular box, and slice it up. Or maybe a dice. Maybe dice is the proper term to borrow from cooking, right? So you got to slice in all three directions. Mince? Is that the right word? I don't know. I should cook more. Okay, so if we do that, then notice the idea of chop it up, add it up, just turns into this expression right here, right? So I have to add up in three different directions. I've got to add up in the x direction. I've got to add up in the y direction. But I've also got to add up in the z direction. So three indices down here, I, j, and k. And on each one, let's see here if I can get, why don't this, I think my pen's messing. There we go. Okay, on each one, on each little piece, the idea is that, and I want to leave this open, flexible, right? I don't want to say what it is that I'm computing. I don't want to pigeonhole myself, only computing mass or only computing, population of fruit flies flying around in there, whatever. Whatever the application might be, there's a ton of applications where on the little piece, the accumulating quantity that I'm going to be adding up will boil down to something times volume, which is just another version of something times size. Here, size is volume. For a double integral, size is area. For a single variable integral, size is width. Right? So basically the same kind of situation, and we're just going to write this expression down with optimism, hopeful optimism that this is going to apply in a bunch of scenarios, and in fact it does. So just like we did before, we're going to give this a name and a notation. This is a triple integral because it's in 3 dimensions. We're going to pick, I'm going to call obvious notation, right? dV, because this little thing here, the whole point of it is that it represents a piece of volume. Okay. How are we doing? Okay. All right, so let's see an example. Now, again, this is sort of an obvious example, but this is kind of what I'm always visualizing when I'm kind of thinking through triple integrals. But the question is, what's the mass in a rectangular box when density varies with respect to all of the input variables? Okay, and first observation I make, and again, I this is my little superstition, I guess you might call it. I find it comforting to write this down. Mass is a double integral dm, not because this is true for all quantities, right? Not every quantity is an accumulating quantity, but mass is. So this is my way of indicating, if only to myself, the whole is the sum of the parts. That's how mass works. Yeah? Is that okay for everybody? Okay. And having noticed that, now the second thing that you have to be careful about and make sure they're actually true before you start writing down integrals is that for each little piece, in fact, I can write the question I'm interested in, namely, how much mass is there in that little piece, as something times volume, right? And now let's just kind of think it out loud now. Is there a thing that I can multiply by volume to get mass? Mass is equal to what times volume? Well, mass per unit volume, aka density. Yeah? Okay. Cool. And then notice, we're in business now. We have a triple integral, and now we just have to figure out how to compute triple integrals, and we'll get to that momentarily. Okay. All righty. So, a quick warning before we go on. There is it's possible to paint yourself into a corner strategically, and I want everyone to be aware of this danger. We've talked about single variable integrals. Well, pretty tersely, but y'all are aware that you can understand single variable integrals as a tool for computing mass of a one-dimensional rod, for example, or you can understand them as a way to compute area under a graph. And we've talked before about pros and cons of these different applications. Fine. Likewise, double integrals you can think of as computing volume under a graph. Sure, fine. Or, just as well, if you prefer, you can think of a double integral as computing, let's say, the mass distributed over a two-dimensional region. Or any of a number of other quantities that you might think of as distributed over a two-dimensional region. Population, again, an easy sort of obvious example. Okay. All right, so let's continue the pattern. How can we visualize triple integrals? And if you follow sort of this pattern, notice you get into dimensional trouble, right? A one-dimensional integral we had been viewing with a two-dimensional picture. A two-dimensional integral we had been viewing with a three-dimensional picture. What do you suppose we would, by analogy, use to represent a triple integral? Well, it would have to be a four-dimensional picture, not on the table, right? It's absolutely inaccessible. Forget about it. It's not going to happen, right? On the other hand, if you use a one-dimensional picture to understand a one-dimensional integral, cool. Two-dimensional for a double integral, then you, by analogy, end up with just a three-dimensional picture. Maybe a little hard to draw, a little artistically challenging, right? But totally accessible and doable, right? More to the point, something you can visualize independent of your artistic ability. You can visualize the idea of something solid in space. So I like to make the observation that this business about thinking of integrals in terms of either area under a graph curve or volume under a graph surface. I mean, okay, it's a crutch of sorts, and that's fine, and has its moment. I myself, as much as I complain about this, I did make some nice use of this to equate double integrals with iterated integrals, right? So, I mean, I'm not saying it's not useful. But if you get too attached to this point of view, and my experience has been that a lot of multivariable calculus students cling a bit too much to this particular point of view, then you paint yourself into a corner where every intuition you have over here you simply cannot be translated for triple integrals. And you will find yourselves not having any sense and any intuition for what triple integrals are. So it's not that you should never view things this way, but I would like to suggest that you should primarily view the sort of general, I'm going to say, accumulation metaphor to understand integrals. And then maybe use the graph point of view sparingly as needed. And again, don't hang your hat on it and don't get too in love with it because it's a problem. Everybody okay? Everybody see it? All right. All righty. The dimension problems continue. So, for example, how do I argue that a triple integral can be turned into an iterated integral, as I'm going to say, of course, we would like to do? I mean, you'll recognize the pattern in this diagram down here. I'd like to kind of strategically be able to use triple integrals just like I did double integrals. There is no concept that I can put in here, I'm going to say in a useful way, kind of like volume. That's where volume was for double integrals, right? And if I were going to fill in this blank on this diagram, it would have to be something four-dimensional, and that's just useless. Okay? So that means a couple of bad things. I'm not going to be able to make that argument or this argument, and therefore I'm not going to be able to give you this version of that argument. Right, so tragically, I'm just going to have to wave my hands and make an assertion, and I hope that you'll trust me on this, that there is another way to make the connection between in this case, triple integral and a triple iterated integral. It's purely algebraic, doesn't require any geometric intuition, but there are some delicate subtleties in it that I don't want to get distracted. That's not what Math219 is about. So I'm going to say, as you would expect, triple integrals can be computed with iterated integrals. And so again, we find ourselves in a scenario where, and reminder, again, none of this, right? Doesn't make any sense. The units don't work out. You have to make arguments concerning quantities that don't make any sense, at least not immediately. Okay, so as you would also expect then, our strategy, the way we're going to answer application problems is the same three-step process. You can directly connect a mass question, for example, to a triple integral, just like we did here, right? Mass per unit volume times volume. Add them up. Right? Once you have a triple integral, you can rewrite as an iterated integral. We're going to spend a bunch of time talking about this second part of the strategy. And then at the end, plug and chug, fundamental theorem over and over again. Nothing to that. I mean, we'll do some examples, but it's pretty much as you would expect. Okay, so here we go. See an example. We're going to start with this right here. How do we? That's going to be most of the work here. But this example does go through all three steps. Notice first, I write mass as a triple integral. Second, I rewrite the triple integral as an iterated integral. Third, plug and chug, and again, that's most of what we're going to go through here will be this business, the actual plugging and chugging. But before we get to that, I have one more little point to make. Is everybody with me so far? Big picture, details to follow. Okay. I emphasize the importance of writing this down right here. You got to give me that triple integral. Right? Because if you don't give me that triple integral, it really looks like you're going straight from an application to an iterated integral, and that doesn't make any sense. Right? Again, reminder, so easy to do. So easy to just jot down this one little thing. Right? That's worth points right there. In fact, if you find yourself on an exam question and you're not sure, how am I going to compute this thing, and the question asks you for mass, just write that down. It's probably worth a couple of points. Just right there. Boom. Right? So don't think of this as an obligation. Think of this as an opportunity for easy money. Right? Make sense to everybody? Yeah, question?
The order of the bounds on the integrals, how do we know, why does the 0, 2 come before though?
Yeah, okay, great question. Okay, so let's talk about that. Great question. Okay, so let's talk about the bounds. Keep in mind, my domain is given to be this. And you got to keep in mind what this notation is. This notation says this is the range of values of my first variable. My first variable is x. And so those numbers are my x bounds. I happen, in this case, for no particular reason, I happen to put my dx slicing in this position here. It was sort of my second one, and so these are the second bounds.
So they line them up. It's just dx doesn't need to be.
This notation up here always means x, y, z. Yeah. This notation exists before I've made any choices down here, and so it has to be x, y, z in sort of standard order, right? But then you've got to organize them so that they match up with the arbitrary slicing order that you've selected. Yeah. So continuing, these are the y bounds, and in this case, because I put dy on the outside, 0 to 2 are my outside bounds. And then just for sake of completeness, that's my z bounds. Z was on the inside, therefore 0 to 1 is my inside bounds. Everybody happy? Good. Okay. The rules for triple iterated integrals are exactly what you would think they are. For any integral, such as this dz integral, any variable further to the outside is to be treated as a constant. So x and y are constants for the purposes of that green inside dz integral. Yeah? Now again, why? Well, okay, that involves me writing a picture that I can't really draw, and so I'm appealing to your sense of pattern here, right? And the pattern is variables to the outside to be treated as constants. And with that in mind, notice that my dz integral of 2z is z squared. And the constants come along for the ride as constants do. Cool? The other little landmine, and again, this is just following a pattern, and it's exactly what you would expect. You can probably even anticipate it. Be careful when you have bounds, such as here, whoopsie, wrong color. Here I have 0 and 1 are my bounds there, right? But it's easy to accidentally forget what you're plugging that in for. And I think it's very healthy to recognize that because these are z bounds, I think it's a good idea to explicitly write z equals. And that will cut down on the accidental, I plugged in my z bounds for my x's or y's or both accidental. Yeah? Everything else is the same. Y'all can do single variable calculus, healthy exercise. Make sure to read through all this. Make sure you follow all that stuff. Okay, now, how do we do it for non-rectangular domains? And again, I can't draw the picture, so what I'm going to again do is just appeal to your sense of pattern, and that it's going to be the same. It just kind of sort of a three-dimensional version of the same thing. And I've got a picture here intent on showing you this pattern. And here we go. So I'm going to arbitrarily do my x slicing first. And a slice perpendicular to the x-axis would be kind of like that. For example, an x slice would look something like this. Cool? Okay. So, with that in mind, if I can find the thing there, here we go. My x bounds, x1 and x2, come from the very first and the very last of those slices. That gives you the bounds. Having identified those bounds, we then fix a slice. So I'm going to fix a value of x here. Right? And for this value of x, the slice looks like this. And for that value of x, we now come back up to the top of this little three-step process, and it all begins all over again with the next variable. Now, my next variable here, arbitrarily, no particular reason, I'm going to do y. So my next slices will be orthogonal to the y-axis. Okay, what does a slice perpendicular to the y-axis look like? Well, it's going to be kind of like that. Now, again, geometric appeal, and by the way, this business here, unavoidably geometric. If you try to do this purely with algebra, without a picture or without visualizing geometrically, ideally both, it's very hard to make an actual argument that actually makes sense. And again, I remind you, it's not about the answer. It's not a question of whether you can guess right? You have to give me an argument. That's what this class is about. It's not about answers. It's about arguments and reasoning. So it's really hard to make reasoning that isn't just unavoidably geometric. Okay, so anyway, here we are. We have our x slices that look kind of like this. And then now I've got my y slicing. I'm taking a y slice of my existing x slice. Right? And now a geometric appeal, the way that slice of a slice works is the slice itself is going to be a little line segment where green and orange combine in an ugly way, don't they? Everybody with me? Okay, so that said, what are the first and last in the usual way? And so now keep in mind, x is fixed. X is not allowed to change. This is what a y slice of my x slice looks like. First and last are, well, the first value of y is whatever that is. The last value of y is going to be, well, whatever that is. All right, first and last y slices of my x slice. And now let's be careful about one thing here, though. Again, common mistake, a lot of students mess up, is to say, okay, I want the lowest and highest value of y over the whole solid. No, no, no. The lowest and value, let's say, for example, the lowest value of y might be some point over here. Right? But, of course, I missed. I'm sorry, bad art. Might be something like that. But notice that lower value of y for this point corresponds to a different value of x that I'm not looking at right now. Right? So while I'm looking at this x slice, while I'm determining my y bounds and how y bounds depend on x, I've got to restrict my attention just to that value of x. Now, fear not, we will get this point. We will get it for a different value of x. And we will get to that different value of x. So we're not going to miss anything. What we need is to know how these bounds depend on which x slice you're looking at. Okay, so you should expect your inner bounds to be functions of the outer variable. Okay. All right, now last part of the process, and of course we're going to see a bazillion examples of this. The last part of the process, so keep in mind x and y are now both fixed. We're going to focus our attention just on that y slice of our x slice. Those variables are now both fixed. And for x and y both fixed, I need to know what's my starting value of z, namely what's the lowest point on that little line segment, And then likewise, I need to know what is the highest value of z, namely what is the top point on that little line segment. Everybody cool? All right, and I will bet you I'm out of time, so why don't yeah, we're out of time. Okay, so we will draw a line right here, and we will pick up here at the after fall break. So y'all have a good fall break. I'll see you on next Wednesday. All right.